Merci Nalini, and thank you for being here. And so yes, I'm a physicist, and I'm interested in quantum chaos. And in particular, today I'm going to tell you about this work that I've been doing here at École Normale a couple of years ago when I was a postdoc with Jorge Curchan. So, and as you see from the title, our goal is to understand what I'm calling low temperature quantum bounds. So these are a set of bounds on some physical quantities like the Lyapunov exponent or some transport coefficients. And these bounds somehow involve some very universal timescales which depend only on the temperature and h bar. I'm going to present a bit better these bounds in the following. So these kind of bounds come and have attracted a lot of attention actually in a very different field in high energy because they're saturated by models of black holes. So all of this seems very far from the topic of the course here. Somehow what we have been trying to do is to understand this kind of quantum bounds on what we call simple models, so on free particles on curved manifolds. And we call them simple models because we consider really baby manifolds, so the simplest possible situations that you can consider. And I'm sure here you've been seeing situations which are much more complicated. So the manifold part for you is going to be almost trivial, but I hope that you may be interested in understanding these problems in more complicated models. Okay, so what are these? What is the outline? So what I would like to tell you is somehow to give you an intuition of what are these quantum bounds and why they could be interesting from a physics perspective, and why we decide to focus on free manifolds, free particles on curved manifolds as a good model where actually interesting things could happen. And then I'm going to show you that indeed in this kind of manifolds, actually one violates the bounds. So these kind of bounds are really enforced by quantum effects, and in these manifolds they are violated. And then I'm going to tell you what are the kind of mechanisms that we find that actually restore the bound in the quantum models. Okay, so this is the plan. So what do I refer to quantum bounds? So the main quantity I'm going to discuss today is the Lyapunov exponent, and kind of a physics intuition of what it is that if the system is classically chaotic, then nearby trajectories separate exponentially fast in time. And an intuitive way to represent this is to consider the derivative of the trajectory to respect to the initial condition. So this is the usual quantity that we say that should grow exponentially fast in time with a rate which we call the Lyapunov exponent. Now, if instead of the derivative of the trajectory to respect to the initial condition, this for a Hamiltonian system corresponds to the Poisson bracket of the trajectory at time t and the position at time 0. Now, why I'm using this Poisson bracket? Because I want to go in the quantum regime, and there have been several ways, several attempts to generalize the concept of Lyapunov exponent in the quantum realm since the inception of quantum mechanics, let's say. And what I want to consider today is the square commutator. So the square commutator, now you see why I wanted to introduce the Poisson brackets, because now if I do a canonical quantization, I can replace the Poisson brackets with the commutator. So now if I want to take the absolute value, I can take the absolute value square. So this object, if I do the classical limit and instead of A I consider x and instead of B I consider P, this object, if the underlying classical limit is chaotic, should grow exponentially fast in time with a rate which is given by twice the Lyapunov exponent. So this quantity indeed was introduced by Larkin and Ovchinnikov in 1969, a long time ago, in order to somehow tackle chaotic superconductors, but was somehow forgotten for a long time. And if we look at this object a bit more in detail, we realize that, so when I say this, you expand this square commutator, you realize that there are some correlation functions which have a very unusual time ordering for physics, because you see this object contains correlators like B at time 0, A at time t, B at time 0, A at time t. So this unusual time ordering has been called out of time order correlator. These kind of correlation functions. And as I said, they were already introduced in this old paper, but then they were almost completely forgotten until Alexei Kitaev proposed really to use this square commutator and to use OTOC, these out of time order correlators, as a probe of chaos also in many body systems. So let me summarize what I wanted to say. We want to define the quantum Lyapunov exponent. And to do it, we consider this square commutator. Why? Because in the classical limit, this becomes the Poisson bracket, which tells me if two trajectories separate exponentially fast. And so if the underlying classical limit is chaotic, this at early times is supposed to grow with the same classical rate. Now, why I say at early times? Because we know that doing the classical limit at the so-called Ehrenfest time, or at least there is a time scale after which we will see quantum interference effects, and this time scale is proportional to the, usually is proportional to the logarithm of the inverse of the Planck constant. So through many body systems without a classical limit, I'm never going to see this exponential growth. So this is not well defined, but if I have a small parameter, a small h bar, or some 1/n expansion that I can do, then I can define this Ehrenfest time. So I really need to think about a model where there is a separation of time scales. So given this somehow this underlying classical nature of this object, it may come as a surprise that actually the rate of growth of this square commutator is actually bounded by quantum effects. So this is a bound which was derived by Maldacena, Schenker, and Stanford in 2016. And says that this rate of growth of the square commutator is bounded above by a constant 2 pi, the temperature over h bar. So where is the temperature coming in? What they consider an out of time order correlator, which is averaged over the thermal density matrix. So this is the Gibbs density matrix, e to the minus Hamiltonian over temperature. And then it's normalized. So they have a proof which is based on some analytic properties of the square commutator in the complex plane, and they're able to prove this bound, which is saturated by models of black holes. And actually last year there was a course by Antoine Georges in which they were discussing, and Subir Sachdev, in which they were discussing precisely this model. Now, this kind of bound...
sorry, can you say, because these commutators, after some time, they become bounded? So
yes. So
how do they define lambda in
yes,
this paper?
exactly. So let me... Okay, so the idea is the following. They study this object, so we want to study it. Okay. Now they don't study really this object, but they study a regularized version. So they take the thermal density matrix, which is e to the minus beta h over z, and then they split it in 4. Okay, so this is just to say what is the specific object that they study. Now, how is this related to the square commutator? So if I take the square commutator, I have to put a minus, so this is the modulus square. Actually, there is a minus in front. So this is equal, let me call this f. this is equal to a two-point function. Let me write it like this. Minus 2f of t. Now, when I say two-point function, by massaging this equation, that there are terms in which a of t and a of t appear nearby, and then there is bb. So I'm leaving space just to say that there are the. So this is it's 2 times because there is time is not out of time order. So then the approximation, the idea is that this object after a small time scale will become a constant. So this basically becomes constant minus 2 f of t. Okay, so the actual object that they study is the constants minus 2 f of t. So they study this object and analytic properties of this object, and then they say that if f of t goes like a constant minus an exponential factor, then this exponential factor is bounded. Yes. Okay. So what they bound is the exponential growth in front, which is here. Now you're saying, how is it possible? Because this somehow at a certain point is so indeed this object. So what you have to consider is c the constant minus f of t, and then this will have something. Then we'll have some exponential growth for some finite time, and then we'll do other things. So they bound only in this time scale.
Okay.
It's a bit. So they study analytic properties of the OTOC, and then they make an assumption. If that function has a growth in that regime, then that rate has to be bounded. Okay. Now the discussion on this kind of bound actually came from or let's say this is a bound. Lyapunov exponent is the inverse of a time scale, and there is another bound which bounds time scales, which is the so-called Planckian bound. Now this bound is a conjecture bound on some physical time scales that says that physical time scale in many-body dynamics should be bounded by T over h bar, temperature over h bar. Now, why this bound? Well, this comes from very different discussions in transport, in which they realized experimentally that many different materials that have very different microscopic properties share the same anomalous linearity resistivity. And this very anomalous behavior, which is obeyed for the so-called strange metals, and this was the topic of the course here, somehow could be compatible with this conjectured Planckian bound.
And what was tau?
Yes, so the definition of tau changes depending on there is no consensus on there is no proper definition on tau. So if you're studying transport, it's the scattering time. It depends a little bit. I'm not a big expert. There is a very nice recent review by Harton and Mackenzie in which they somehow try to explain the complexity of defining such a bound. Okay. But I just wanted, and they somehow conjecture this bound because there is another almost proof of a bound on the viscosity, the shear viscosity over well normalized with some entropy. And somehow this is a bound which is valid for relativistic plasmas, but is of the similar form of this Planckian bound. There is more, the definition in this case is a bit more stringent than this kind. But they have a very similar form, and I think this is why everyone in condensed matter got very excited about this Maldacena, Schenker, and Stanford bound, because it was the first time that they somehow were able to prove a bound of Planckian form, because you see there is also T over h bar. But again, there are some people that don't even believe that this kind of Planckian bound should exist. Okay. Now, what I wanted to, the idea of our work and somehow of other kind of attempts that we have been doing trying to understand these features is that if such bounds should exist, then it cannot be like some property of analytic functions or it shouldn't be a property of black holes, but it should be possible to understand them for simple quantum mechanical problems. So if it's a bound of quantum effects, we should be able to see it in some kind of in simple models. And so the idea is what's the simplest quantum mechanical situation in which this kind of bounds could have a non-trivial effect or could have some effect. If we want to, so let me write it again so we don't have. We want to study these bounds which happen on a time scale which is, I just realized now that I've been saying before beta, so beta I always mean with beta the inverse temperature. So for instance, lambda is much smaller, 2 pi beta over h bar, so So temperature, okay, no, I use temperature. Okay, so if I want the bound to be significant, I have to go to very low temperature. So this bound classically, if I just send h bar to 0, is trivial because it's not bounding anything. If I want the bound somehow to be effective, I have to consider temperatures which are of the order of h bar. So I have to go to very low energies. Okay, so the idea is that I should think about a quantum model or a classical model which has some sort of chaotic dynamics even at the lowest energies, so at temperatures of the order of h bar. And now to do this, if I think about a classical, an Hamiltonian in the classical limit, I can think about some particles which are moving with some potential. And now it's clear that if the potential has an isolated minimum, then I'm not going to have any interesting motion because now if I consider quantum fluctuations, when there are isolated minima, the quantum fluctuations only induce some oscillations on top of the classical ground state. So what we need is somehow a classical model which has a flat manifold of minima, where somehow the lowest excited states, when I go at very low temperatures, can have chaos. So I need to consider a model which can host the chaos up to the lowest temperatures, where my excited states can host chaos. And there are two examples of such a kind of models, so billiards and manifolds. So why this is the case? Well, for you it's very well. So for you it's normal. So because if this kind of phase space is just determined in terms of position, so of coordinates. So changing energy amounts just in rescaling the velocity. So I'm always going to have chaos up to the lowest energies, because by decreasing the energy, I'm just decreasing the velocity, but I still have chaos. And now this kind of with this kind of choice, somehow I can focus on manifolds, because the two of them somehow coincides. Well, we didn't know this, but then we read the Arnold. Okay, so we're going to focus on free manifolds, free particles on manifolds to study these kind of problems. Okay, so let me, this is more a slide for physicists, but why in physics also this kind of problems, this kind of models could be interesting is because both our spheres could be pictured as billiards, but in particular I want to tell you about spin liquids. So spin liquids are systems in which you have for instance, two-dimensional arrays of spins which interact through some antiferromagnetic interaction, but the ground state of these spin liquids are frustrated, so you have you have many possible ground states. And in particular, for instance, I didn't write here the Hamiltonian, but there are many kind of classical spin liquids where the ground state is identified by asking that the sum of the spins on each plaquette, okay, sums to 0. But this is just to say that there is a large class of models which have an exponentially degenerate manifold of minima, so that could be pictured in principle as manifolds. But I'm going to go back on this because you will see. Okay. To rephrase, I introduced you what are these quantum bounds, in particular the one on the Lyapunov exponent, and then somehow the question that now we want to address is how do these bounds read when studying free particles on curved manifolds, because this should be the simplest models which can host chaos up to very low temperature. So this is somehow the motivation. So let me just set some notations. So what we want to study is some dynamics with some metric here with Jij. And now what one can always do is somehow to consider dimensionless variables. And you will see why this is useful for us. So I'm going to call R, large R, the characteristic length of the geometry. And so if this could be, for instance, the radius of curvature of your manifold. Okay, so if I do this, so I can rescale everything, and then when I consider a single particle which moves in a manifold, the classical Hamiltonian reads just like this. So this is 1/2 the mass r square, and then there is some dimensionless moment, and now from now on the metric is going to be dimensionless, will only depend on dimensionless parameters. And now the trajectories in this case are geodesics on the manifold. Okay, so this is the classical limit, and for the quantum dynamics what we have to do is that we have to solve the Schrödinger equation, and now we can also make it dimensionless. We have to add an h bar square, and then the evolution is given by the Laplace-Beltrami operator, which is how the derivative acts on this manifold. So now what is the characteristic length scale of the quantum problem? The characteristic length scale is the de Broglie length. So this is the length scale of a particle at temperature T. And what we know is that in the classical limit, the Fermolier length scale is equal to 0. So we are in the classical limit every time all the distances, all the length scales are much bigger than the thermal de Broglie length. But when this length scale becomes comparable with this characteristic length scale, something is going to happen. So somehow we have, just to repeat, we are studying the classical dynamics of manifold. There is some geometric property, there is just some geometric length that quantifies the curvature, for instance. And we are going to compare it with, the classical limit is when this is much bigger than the thermal de Broglie length. Okay.
Can you repeat the interpretation of this thermal de Broglie?
Of the de Broglie length. So, for instance, is the length scale, let's say, at which in which you start seeing interference between the particles. Another. Yeah, in which the quantum particle. So it's introduced in this particle wave duality, and let's say is the wave of the particle. It's the wavelength of the particle. So if this wavelength is very small, it means that it's you don't see that it's a wave, but just that it's a particle. Okay. But why do we like these two scales? Because now in these models, since there is this invariance, this let's say scale invariance, we can make use of dimensional analysis and show that at the end everything is the dimensionless quantities are a ratio of the geometric and the quantum length. So how to do this? So what we are studying is the quantum problem. So we have to look at the observable at time t, which is given by the evolution. So this is the time-dependent observable. So I'm applying u and u dagger. So this is the Schrödinger equation applied to an observable. And then I can use the rescaling of the Hamiltonian, and one can simply see by plugging these two quantities that basically I have something which is completely dimensionless. The time is rescaled by this Planckian time that I showed you before. So this kind of models are automatically Planckian in the sense that there is only the energy that appears. So the characteristic time scale is h bar over t. And then if I look at observables at these time scales, so in units of the Planckian time, then everything is only a function of r over L. Now this I realize it's a bit abstract, so the only thing I want to say is that since these kind of models are characterized only by geometry and energy, basically, the physical quantities, the dimensionless physical quantities can be rewritten only in terms of this ratio between these two length scales. And now, for instance, if I look at the Lyapunov exponent that we derived before, the idea is that the dimensionless Lyapunov exponent, so the one that you get, so if I multiply here by h bar and I divide here by h bar, so the quantity that should be bound, that should be dimensionless, this again is a function only of the ratio between the geometric and the quantum length. Okay, but so what is this saying? Now, a picture to say what I just said is if I look at this dimensionless quantity, I should imagine that this is only a function of r over this quantum scale, and we said that we are in the classical regime when this number is very large. Okay, and the quantum bound is saying that this dimensionless Lyapunov should be below pi. So this is what my bound is saying. That's a quantum effect. This quantum bound allows me to be only here. Okay. But now, if I do the classical limit on this kind of models, what I find is a violation of the bound. So how to do the classical limit? It's again in the appendix of Arnold. Basically, chaos between two geodesics is defined from how two geodesics separate with the path length, and this r is the characteristic length scale at which two geodesics separate. And now, if I want to pass from the length scale to time, because the Lyapunov is usually a time quantity, I have to rescale with the velocity. But now the velocity is square root of e, because it's a free particle. So using the equipartition theorem that the energy is equal to t, I obtain that the velocity is square root of t. So basically the Lyapunov exponent should be square root of t. And so when I divide it by t again, I obtain 1 over square root of t. Now, okay, all the details are not important. So what from the slide, the idea is that in this kind of models, we show they should depend only on r over this thermal length scale. But what we find classically, just using dimensional analysis, is that at low temperatures, there is a violation of the bound. Because just following from this property that the classical Lyapunov exponent on manifolds should be square root of t. And so here there should be something quantum that happens when these two length scales are of the same order, which somehow is enforcing the bound to apply. So this was somehow the starting point. So then what we will want to do is to understand how quantum effects arise in enforcing this bound. So the point to remind is that, okay, so the Lyapunov exponent is just a function of this ratio between these length scales, and the classical Lyapunov is square root of t. But this is it's a very old result. Now let me tell you why we got, and other people got somehow thought that this was a good starting point, because actually in a numerical experiment in this kind of spin liquid that I was telling you before, they found that the classical Lyapunov exponent was scaling with square root of t. So now they consider a classical many-body dynamical system, which is this classical spin liquid. Now all the details are not important, but what they find is that there is a square root of t Lyapunov exponent, so there is a violation of the bound at very low temperature, classically. So somehow the square root of t that comes from manifolds applies to this kind of many-body spin liquids. So this is a paper by Meusner, Bhattacharya collaborators. So this somehow pushed in the direction, okay, let's see then in the simple case, so not studying the spin liquid, but let's simplify the model as much as we can and trying to understand how quantum effects arise in that model. Okay, which brings me to somehow discussing what are the possible scenarios. And we somehow point out three kind of effects that could play a role. Now, the first effect is somehow a trivial effect, which is when, so I call it a size effect, which is that when the Broglie length is the order of the whole volume of the system size. In other words, or another way I see it, if you're studying the spectrum, so here you have the ground state, then you usually have some excited states, then here they become very dense, no? So this problem is when you look too low in energy, and so you're seeing the discretization somehow. So you cannot have a classical limit. This is a situation in which basically the Ehrenfest time is too small. So you cannot really do a classical limit, let's say. And we would say that when the quantum fluctuations are of the order of the system size, so the quantum effects are huge, nothing is really happening. I mean, you cannot see even you cannot even define a classical limit. Okay, but this is trivial, and somehow we want to study models in which there is a classical limit, yet the bound could be enforced non-trivially. Okay, so then to study this kind of systems, what we want to consider a toy model, so this baby manifold, and this is the surface of constant negative curvature, and so which is the most chaotic manifold somehow that in principle is non-compact, so one is unbounded, so what we want to do is to make it bounded and somehow to construct a toy model which we could understand. So one can represent the metric in terms of polar coordinates, where now tau somehow, this is represented on the stereographic projection onto the Poincaré disk. And now to somehow to make it compact somehow in a brutal way, what we say is that we don't let the radial coordinate to go to infinity, but we somehow make it finite. So we impose that in the Poincaré disk there is the Poincaré disk ends at some tau, finite tau O x. Okay, and then we add a cylinder, a flat cylinder on top of it. Now you may wonder why we add a ceiling. So now this is a bit of our taste, why we construct exactly, or we look at this toy model. So what we wanted to see was the effect of the curvature itself. So whether the curvature was playing a specific role in enforcing these bounds. And so we add something flat, which we know is non-chaotic, somehow to see really the effect of the curvature. Then another reason is that somehow there are ways to make this manifold compact by setting specific periodic boundary conditions, but somehow we went for this more easy approach. Okay, but now I have this cylinder and I put an infinite wall on top of this cylinder. So I have two parameters. I have now the length of the chaotic region, which I'm calling this 2x. So this should be a number which is smaller than 1, because at the boundary of the Poincare disk there is infinity, and it should be smaller than 1. And then I have the length of the cylinder, and I can play with these two parameters to make the volume of the system very large. So somehow to go here in the middle of the spectrum.
And you don't really care if the place where you glue the cylinder to the pseudosphere is singular?
We don't really care, no.
You don't care?
No.
Okay.
But, so what we do from the... okay, I'm going to go back to this question, but maybe... yeah, in one slide. So then the classical limit of this model is almost chaotic, in the sense that actually, the classical Hamiltonian actually conserves also the angular momentum. So the dynamics is integrable, but it's exponentially unstable, in the sense that I have that the geodesics separate exponentially fast in what I call the cone, so in the pseudosphere. But then they come nearby again because the angular momentum is conserved, so they have this flat. So what we can do is that we can add an infinitesimal perturbation to somehow break the conservation of the angular momentum, and then retrieve the real chaoticity of the model. So this is an issue, more of a technical issue, but okay, there is this problem. So what we do basically this is just the picture of the evolution of this model with the perturbation. We see somehow this chaotic geodesics now on the Poincare disk. And then we check other things, that our classical limit is really chaotic. So we check that the late time distribution coincides with the uniform distribution in this curved space. And then also that the total Lyapunov exponent is the one that we know from Arnold, let's say, so from the rescaling with the velocity. So the classical Lyapunov exponent in the chaotic region, so in the pseudosphere, should be square root of 2e over mu r square, where now in the pseudosphere large r is really the curvature of the system. But now the total Lyapunov exponent is going to be given by the chaotic one times the ratio of time which is spent in the chaotic region and the total time. So this is this ratio of volumes.
So you say this small perturbation is needed so that your system is chaotic?
Yes, because you see, otherwise there is energy and angular momentum which are conserved, and so the model would be chaotic if I only was looking in a pseudosphere, but then there is this conservation, so we need... so what we checked numerically is that the kind of form of the perturbation, which now will depend on the angle, is absolutely inessential. So we can play with a very small perturbation and retrieve the real...
And why do you prefer this model than, for instance, a Sinai billiard? Or?
Because we thought, at the beginning we thought that this was somehow simpler.
Okay.
No, I mean, I guess that what you will see is that there is a simple way to see, but maybe there is a simple way we have here to see how the curvature is acting, and maybe there is a more elegant way to see it in a different context. Okay, so now we can study the quantum version, and when we study the quantum version, this problem can be solved exactly. I mean, one can find the eigenfunctions and the eigenvalues simply by finding the solution in the chaotic region in the cylinder, and then matching and implying the continuity of the wave function. So this is what we do, and we don't really think too much about the possible. And indeed we find then smooth wave functions which are continuous. So we solve the problem like in a class of...
This is without the perturbation?
This is without. So these are the exact, thank you, these are the unperturbed wave functions. So then what we do, basically, we find the unperturbed wave function then numerically. I mean, for the results, when we do the numerics, we write the perturbed Hamiltonian in the basis of the unperturbed wave function, and then we solve it, we diagonalize it numerically. But these unperturbed wave function basically have all the information about the dynamics. So what we're saying is that the whole information is contained in these eigenstates. The one only has to somehow mix them a little bit with this perturbation. That's the idea. Okay, so we add the perturbation also in this case, and then we look that actually if you look at this square commutator on a very high energy eigenstate, so if I put myself here, then and I pick some n0, and then I compute the square commutator averaged over here, I get exactly the classical result. Okay, so we do this numerically, so for different kind of eigenstates, and we find that, so here there is no fitting parameter, this is really the Lyapunov exponent that we calculated from, it depends only on the energy at which we are computing these things.
And the observable is...
Yes, this is the radial coordinate. But it should be in essential, actually, because this should all grow exponentially. Okay, so this was somehow the classical part, in which we are at very high energy. So what happens if we start lowering the energy? So in this class of models, the Laplace-Beltrami operator somehow creates a potential which is proportional to h bar square, which depends on the curvature itself. So somehow I can rewrite the Schrödinger equation with the Laplace-Beltrami on a transform wave function phi, which is simply given by the Schrödinger equation times the determinant of the metric of the power 1 over 4. This is the quantity that integrates to 1, so the one that has the classical limit. And so if I rewrite the Schrödinger equation in this way, I find that there is a classical piece, and then there is, I don't know, a quantum potential, which is proportional to h bar square, and depends on the curvature, and then some logarithm of the... So I guess this is something very well known. And so what is the shape of this repulsive potential? So basically it is attractive in the case in which the curvature is positive, but if the curvature is negative, and the negative curvature is what is creating chaos, the potential becomes repulsive. Becomes repulsive. So in this kind of geometry that we are studying, in which we have a chaotic region which is curved and a flat region which is non-curved, a flat region which is non-chaotic, okay? The particle, if I go at low energy, will start to experience a repulsive potential which is induced by the curvature. Okay, so in other ways, if I'm here, so if this is the spectrum, there is somehow this minus h bar square k over 4, but k is negative, so this is 1 over 4 square. Okay, there is this potential here that is repulsive. So somehow, when I hit this energy, or when I get closer to this energy, the particle doesn't want to be anymore in the chaotic region, because somehow it's repelled by there is a potential here. So with these exact eigenstates that I was showing before, this is something we can check. So if we go at very high energies, I see that the particle is uniformly distributed in this geometry, but if I lower the energy, then the particle will want to stay only in the flat region and then does not enter in the chaotic region. So this is an evanescent wave if I go nearby this gap. So why this is important for us? Because if I use this sort of classical picture in which I have a particle that is moving so it's a semi-classical picture in the sense that I have a particle which is moving, but then I say that it can feel this potential proportional to h bar. So what it means is that when it will start to feel this potential, it will slow down, because the velocity now in the chaotic region is proportional to the square root of E minus the gap, minus the potential. And so by doing so, if I put now this new velocity in the kind of Lyapunov exponent, which just is the velocity over the length scale, I find that the result that I derived before is somehow, which was giving me this violation, is somehow modified by this square root of the dimensionless energy minus the dimensionless gap, 1/4. And so somehow it will have a maximum and then it will vanish exactly at this at the gap of the at the value of this effective potential. So let me summarize what we say. So we have these manifolds in which we check also for this our toy model that the particle is chaotic, has the same properties as the classical limit, which has a Lyapunov exponent which should diverge at low energies. And now we say, okay, but what are the quantum effects? It is well known that the particles, that the curvature induces a repulsive potential. And I'm saying that this repulsive potential, which is induced by the curvature, it's somehow also slowing down the particle. So in the most curved regions, the particle will experience this chaotic potential that slows it down, and so it diminishes, it decreases the Lyapunov exponent, and this is what enforces the bound. So this somehow...
but I'm not sure I understood. The bound is compatible with the Maldacena-Schenker?
Now, yes, somehow. Before it was violating, but now this is... So classically it would violate, but now, okay, it's not that it's violating Maldacena-Schenker and Stanford, it's because I'm using the classical result even when I should not. So when I know that quantum effects become important, and I say that the first approximation I can think about this potential, and this potential, it's a way to explain why the bound is not violated, because it's slowing down the particle and makes it...
And the bound that you get, because we are not used to following all the physical constant, but the bound that you get is much smaller than the Maldacena-Schenker, or does it saturate? It's smaller because, okay, no, thank you, because here, so basically here there is a factor which is also proportional to the ratio of volumes, so it depends on the geometry. So it's not, we are not very close. So there could be the construction of a smarter model which saturates the bound. So it depends on like the two parameters.
Yes. Because for us, somehow the total Lyapunov exponent is given by the ratio of the volume of the chaotic region and the flat region. But this somehow brings me to somehow the open problems in our approach. So this I can skip it. Okay, let me stay here. Okay, so now I am explaining everything with the presence of this repulsive potential and the fact that if I go below this repulsive potential, my particle will want to stay only in the flat region. Okay. But now you can wonder, but what happens if I don't have any flat region? So this depends a lot on how I'm constructing this model. So what happens if the particle is only... So this was like a very hard... So we dedicated most of our time trying to understand what happens, and I think our answer is honestly not very satisfying. Because at the beginning what we believed is that if, for instance, I only have the chaotic part, then there is always a gap between the uniform solution, so the uniform wave function, and the first excited state. And this gap is usually in dimensionless variable 1/4. But then we realized that the uniform solution depends on how you are imposing the boundary conditions. So it's not true that it always happens. So we were at the beginning very, very happy that there was always this gap that was saving us, because if you have a gap, so the situation is now the following. You have the uniform, then you have the gap, and then above this you can have
all this. And so we were saying, okay, I can never go really to zero temperature, so because there is this gap. But now if this is not here anymore, I can go basically to zero temperature and have the bound. So we somehow could not resolve this dependency on the presence. And then we started to think about some sort of other, okay, this we skip. Some sort of other effect. So we thought, okay, what happens if I only have a particle and there is only the chaotic region? Let us think about some other effect that could take place. So we start. The idea is that another way to evaluate this classically, this derivative of the length with respect to the initial condition is to consider the square of the radial coordinates in time divided by the angle derivative. And I should use this, sorry. Okay, so it's to use this kind of square of this hyperbolic sign. So then we cooked up a quantum equivalent of that. So I spare you the details, but basically we find that if we do this, there is also something happening something is happening exactly when the de Broglie length becomes of the same order of the length scale, but it's not that the particle slows down. On the contrary, you cannot define a Lyapunov exponent anymore. So somehow, if there is no curvature, that if there is no potential, so if the particle is not slowing down, you lose the definition of the Lyapunov regime at all, because you find something which grows super exponentially.
So I'm not sure I got what is the model here.
So it's the same model, but now you remove the flat space. So it's
infinite?
Yes, it's infinite, yes. Is infinite. But in the infinite model, so you assume infinite model, and then you compute, like you have a Gaussian with packet which is evolving, and you just consider the evolution of this object. So you just assume that the square commutator should be given by the exponential of the radial coordinate. And then you find something very strange, that there is a linear exponentially fast regime, which is the one that should give the Lyapunov exponent, but then there is also a super exponential term, which makes the problem not well defined. So in this case, there is no Lyapunov regime, so we cannot, but this is a bit of a bad fix, because somehow we are saying that in this kind of situations, you should not think about the Lyapunov exponent at all. Well, it would have been better to have something, but we couldn't find it. Okay, so with this I think I'm almost ready to conclude. I just wanted to mention something about the viscosity and in general about transport coefficients. So we didn't really went through this part a lot. I just want to mention something that because we didn't know enough about dynamics of manifolds, I think. So viscosity and general transport coefficients, they can be thought about resistance in some deformation. So in particular, thanks to Kubo formulas, we can always compute transport coefficients like the viscosity as integrals of correlation functions which depend on 2 times. And now there is a famous, let's say, approach which transforms this kind of integrals into problems of diffusion. So instead of having a current here, you define an Elfland moment. Okay, it's basically the integral of this current, and then you can compute the transport coefficients just as diffusion rates on your manifold. So an idea to somehow compute viscosity and transport in this kind of manifolds is to look at multiple connected surfaces and then count the number of diffusion around the handles. So this is just a way to do it, but yeah, we didn't pursue. But what we did is a similar analysis as a dimensional analysis as the one I explained you for the Lyapunov exponent. Now again, the details are not important, just this plot. I have the dimensional as now viscosity, and again we can show that this should be only a function of the ratio between this length scale, and but now at in the classical regime, everything is fine. So we find the proper, the classical limit is above the bound. But then if I go at very low temperatures, or let's say when the length scale become comparable, there is a violation, again, also of the bound on the viscosity. And so one, in this case, also would like to understand how quantum effects happen in this case. But again, this is something we do not pursue, but it's kind of similar to what I described it before. Okay, so to summarize, I hope that I conveyed the idea that there are these bounds that are somehow mysterious, that are coming from a very different, motivated from a very different community, but that if we study manifolds, then just as a result of the scaling basically of the velocity with the energy, we find that all the dimensionless quantities are just a ratio between the geometric length and the quantum length, let's say. And that in this kind of models we have violations of these bounds, but then there are some effects that restore the validity of these bounds. And in particular, we discussed more in details the effect of these repulsive potentials which are induced by the curvature itself. Okay, and this is what I skipped. And also I want to somehow state why somehow we stopped or where we were not able to go, which is understanding somehow a bit better how this gap influences the problem, whether there is a reason why there always should be a gap in physical models. So, because this for us was quite a good ingredient to restore the bound. And then there is something also that is still open, is to study transport and diffusion of manifolds, and I don't know what is the progress in math to do so. And then something that we haven't been doing, but we know that Mössner and Bhattacharjee have new results, is somehow to use these approaches to study macroscopic models such as spin liquids.
So macroscopic means large number of
large number of particles. So what I know from what they said last time we met is that they have some numerical results on quantum spin liquids now, and where they see, so they were seeing before the square root of t, but now they find that there are different regions which have something which could look like a curvature that explains somehow why the bound is there. But I think we have to wait a little bit. Okay, so with this, I thank you for the attention and for the invitation.